You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Security Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. System resilience refers to the ability of a system not only to remain available, but also to recover gracefully when problems occur. While availability is often measured in terms of uptime percentages, resilience extends further by considering how systems degrade under stress, how quickly they recover, and whether users can still perform essential functions during disruption. For example, a payment platform may remain partially functional by processing credit card transactions even if reporting features are unavailable. Resilience recognizes that failure is inevitable, and the goal is to ensure services degrade gracefully and recover predictably rather than fail catastrophically. Redundancy is a foundational strategy for resilience, but it comes in multiple forms. Component redundancy involves duplicating critical hardware, such as power supplies or network cards within a server. System redundancy means deploying multiple servers or clusters to take over if one fails. Geographic redundancy extends further, spreading workloads across data centers or cloud regions to withstand large-scale disruptions. For instance, a bank may mirror customer databases across two separate regions so that operations continue even if one data center goes offline. Each level of redundancy increases resilience, but also adds complexity and cost. State management plays a central role in determining how resilient services can be. Stateless services do not store session data locally, allowing requests to be routed to any server without concern for persistence. This design makes it easier to scale and recover after failures. Stateful services, however, maintain context such as user sessions or database records. If state is lost, recovery may be more complex. For example, a streaming service with stateless front-end servers can reroute traffic easily, while its stateful media catalog requires replication strategies to ensure consistency. Designing for resilience requires balancing these models carefully. Recovery time objective, RTO, and recovery point objective, RPO, are two key metrics in resilience planning. RTO defines how quickly a system must be restored after an outage, while RPO specifies how much data loss is acceptable in terms of time. For example, a retail website may have an RTO of 30 minutes, meaning it must be back online within half an hour, and an RPO of 5 minutes, meaning no more than 5 minutes of sales data can be lost. These metrics guide design decisions, helping organizations prioritize investments in replication, backups, and automation. Capacity planning ensures that systems can handle both normal traffic peaks and unexpected load during failure scenarios. Headroom must be built into systems to absorb traffic surges or redistribute workloads when components fail. For example, if one data center in a multi-site configuration goes offline, the others must be able to absorb its load without collapsing. This requires monitoring utilization trends, forecasting demand, and over-provisioning capacity strategically. Failing to plan for headroom means systems may run fine in normal conditions but collapse during crisis, undermining resilience. Load distribution strategies provide flexibility in balancing resilience with efficiency. In active-active configurations, multiple systems handle traffic simultaneously, providing both performance and redundancy. In active-passive setups, a secondary system remains idle until the primary fails. For instance, an online retailer might run active-active web servers across two regions to maximize throughput, while a backup database runs in active-passive mode to reduce costs. Each strategy has trade-offs in terms of complexity, cost, and recovery time. Selecting the right model depends on business priorities and acceptable downtime. Circuit breaker patterns are design mechanisms that prevent cascading failures when systems become overwhelmed. Just as an electrical circuit breaker cuts power to prevent fire, software circuit breakers stop requests to failing services and route traffic to fallback systems. For example, if a recommendation engine is unresponsive, a circuit breaker may return generic product suggestions instead of repeatedly trying to query the failing service. This prevents system-wide slowdowns and allows degraded functionality to continue while issues are resolved. Circuit breakers illustrate how resilience depends not only on redundancy but also on intelligent failure handling. Fault isolation limits the blast radius of failures, ensuring problems remain contained rather than spreading across the system. Isolation can be achieved through segmentation, such as deploying services in separate containers, clusters, or zones. For example, if one microservice in a banking application fails, fault isolation ensures it doesn't crash the entire platform. Limiting dependencies between components, using clear boundaries, and restricting privileges also reduce the risk of cascading impact. By designing systems that fail in isolation, organizations improve overall stability and resilience. Monitoring health metrics is necessary but insufficient on its own. While metrics like CPU usage, memory, and network throughput reveal system health, business-level service-level objectives, SLOs, provide more meaningful resilience indicators. For example, an e-commerce site may meet all hardware health metrics but still fail its SLO if customers cannot complete purchases. Monitoring must bridge both infrastructure-level metrics and business-level outcomes. This dual approach ensures organizations measure resilience not only in technical terms but also in the ability to deliver real value to users during disruptions. Chaos engineering and fault injection testing validate how systems behave under failure. Instead of assuming resilience, teams deliberately break components in controlled experiments to see whether services degrade gracefully. For example, Netflix's Chaos Monkey randomly terminates servers in production to ensure redundancy strategies work. Fault injection can simulate network latency, disk failures, or corrupted data. These tests provide evidence that designs function as intended, uncover hidden weaknesses, and build confidence in recovery processes. Chaos engineering shifts resilience from theory to proven practice. Graceful degradation strategies allow systems to maintain partial service when full capacity is lost. Instead of going completely offline, services reduce features while continuing core functionality. For example, a video streaming platform may temporarily disable high-definition options but continue streaming in standard definition during load spikes. Graceful degradation prioritizes essential features, maintaining usability and trust even when resources are strained. This approach recognizes that partial service is far preferable to total outage, especially when customer-facing applications are involved. Resilience is ultimately a discipline of design and testing rather than simply redundant hardware. While backups, failover systems, and replication provide tools, the true strength lies in how these are integrated, validated, and managed. Resilience requires foresight, careful architecture, and continuous testing to anticipate failures before they happen. For example, without testing, an expensive failover cluster may fail due to misconfiguration. By treating resilience as a lifecycle discipline that combines redundancy, monitoring, testing, and governance, organizations ensure systems remain dependable in the face of inevitable disruptions. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Data replication is a core component of resilience, but it comes with trade-offs. Synchronous replication ensures data is written to multiple systems at the same time, guaranteeing consistency across nodes. However, this can increase latency and impact performance, especially across distant regions. Asynchronous replication reduces latency by allowing writes to occur locally before updates propagate to replicas, but this creates a window where recent changes may be lost in a failure. For example, a global e-commerce site may use synchronous replication for transactions within a region but asynchronous methods for cross-continent data to balance speed with resilience. Rolling upgrades, canary releases, and blue/green deployments are strategies that preserve uptime during changes. Rolling upgrades gradually update subsets of servers, ensuring others remain online. Canary releases push updates to a small group of users first, reducing impact if issues arise. Blue/green deployments maintain two environments. one live, one staged, allowing instant switching between them. For example, a financial platform may use a canary release for new transaction software, ensuring errors affect only a fraction of users. These patterns minimize disruption, aligning resilience with continuous improvement. Disaster recovery, tabletop exercises, and runbook validations prepare organizations for real-world incidents. In tabletop exercises, teams walk through hypothetical disasters, testing, decision-making, and coordination. Runbook validation confirms that documented recovery procedures actually work when executed. For example, a team may simulate a ransomware event, following recovery steps to restore backups and validate operations. These practices uncover weaknesses, ensure readiness, and build confidence. Without them, organizations may have plans on paper that fail under pressure. Regular exercises transform theory into muscle memory. Monitoring guardrails and escalation policies provide structure for responding to availability incidents. Guardrails define thresholds for acceptable performance or error rates, while escalation policies dictate who is notified and how quickly when limits are breached. For instance, a 2% error rate might trigger automated mitigation, while a 10% error rate escalates directly to engineering leadership. Clear guardrails prevent delays, ensuring incidents receive the right level of attention at the right time. These frameworks provide consistency and predictability in managing resilience events. Cross-region and multi-site deployments improve geographic resilience by ensuring services survive localized disruptions. A cloud-hosted application might run across 3 regions, allowing operations to continue even if one region suffers an outage. Multi-site deployments within a country can ensure resilience against natural disasters or utility failures. For example, a healthcare system may host patient data in 2 cities, replicating records to guarantee access during emergencies. Geographic diversity strengthens availability but requires careful synchronization, monitoring, and governance to maintain consistency across distributed sites. Cost versus availability trade-offs are inevitable in resilience planning. Achieving 5 nines, 99.999% availability often requires enormous investment in redundant infrastructure, which may not align with business needs. For example, an online streaming service may tolerate brief outages but invest heavily in fast recovery, while a hospital system may require near-continuous uptime for life-critical equipment. Aligning spending with business risk appetite ensures resources are applied rationally. Resilience is not about eliminating all risk, but managing it in proportion to the consequences of failure. Dependency mapping identifies hidden single points of failure across systems. Complex architectures often depend on shared components like DNS providers, authentication systems, or storage clusters. If overlooked, these dependencies can undermine otherwise resilient designs. For example, a global retailer may replicate its applications across regions but still rely on a single identity provider. Mapping dependencies reveals weak links, enabling mitigation such as provider redundancy or alternate paths. By visualizing interconnections, organizations reduce the risk of blind spots in resilience planning. Fast rollback capabilities and immutable artifacts shorten recovery times during failures. Immutable artifacts, such as pre-built containers or signed binaries, ensure systems can be restored to known good states. Rollback mechanisms allow quick reversal of failed deployments or configuration changes. For example, if a new software release causes outages, rollback tools return services to the prior version within minutes. These capabilities reduce reliance on lengthy troubleshooting during crises, focusing instead on restoring service quickly while root causes are investigated. Backup validation and restore testing are essential elements of resilience hygiene. It is not enough to create backups. Organizations must verify they are recoverable. Periodic restore tests confirm data integrity, validate procedures, and build staff confidence. For instance, restoring a random database backup each month ensures that recovery steps work and that data is usable. Without validation, backups may provide a false sense of security, only to fail when needed most. Consistent testing ensures that recovery is reliable, not just theoretical. Capacity and resilience planning must be revisited regularly as systems evolve. Growth in user traffic, architectural changes, or new business priorities may invalidate old assumptions. For example, a capacity plan built for 1 million users may fail when the platform scales to 10 million. Periodic reviews update RTOs, RPOs, redundancy models, and monitoring thresholds to match reality. By treating planning as a continuous process, organizations prevent resilience gaps from quietly emerging as systems scale and change. Resilience is ultimately a lifecycle practice encompassing design, testing, operation, and improvement. Initial design establishes redundancy, monitoring, and recovery models. Testing validates assumptions through simulations and chaos experiments. Operations maintain guardrails, monitoring, and escalation paths. Continuous improvement ensures resilience adapts as threats and systems evolve. By embedding resilience into every phase of the lifecycle, organizations transform it from a static capability into a dynamic discipline. Resilient systems are not defined by perfection, but by their ability to adapt, recover, and continue providing value under stress. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.